All right, guys, so your last anatomy and physiology lecture ever. Yay, good job. You made it. So we talked through a lot of general stuff about the kidneys. Now we're going to go ahead and get into lots of different specifics. So we'll start by talking through the tubules and all of the reabsorption that happens there in the tubules and all the details that we can about that. Then we'll talk about filtration and all those details as well. So when we look at the renal tubule, remember the whole point here is to kind of fine-tune the urine, right? We just filtered everything based on size. Now we need to perfect it, make sure that we're just getting rid of the wastes. We do that via reabsorption out of the fluid back into the body, and then secretion into the fluid. When we look at the kidney tubule, remember that it's lined by cells, right? So if we have a tube here and all of this filtrate, all of this fluid and solutes is going through it, this is lined with actual cells, right? Tubular cells. And the cells differ in different areas of the tube. That's how the functions differ, right? Depending on the cells that we have present, depending on the transporters that we have there, the tubular cells are able to do different things. But in general, what happens when we're reabsorbing something back into the body is that this tubular cell will absorb whatever it is we want to take in. Okay, so it could be a nutrient like glucose or amino acids, it could be an ion, it could be water. But whatever it is, we absorb it first from the tube into the cell that's lining it. Then from there, it exits the tubular cell and it goes to the surrounding interstitial fluid. But it doesn't stop there. Remember, we need to end up getting everything back into the bloodstream where we started. And that's where the peritubular capillaries come in. Oh, that's not peritubular fluid, it's down here. That's where the peritubular capillaries come in. Remember that surrounding the tubule, we have another set of capillaries, either the peritubular capillaries, or if we're looking at the really long loop of Henle, remember we had those long vessels called the vasa recta. But in either case, it's going into the bloodstream. Okay, so it's kind of the reverse. We started in the blood and we pushed things out into the fluid, and now the opposite's happening. The things that we want to reabsorb go into the cells that line the tubule, then into the surrounding interstitial fluid, and then ultimately they'll enter into the bloodstream again. Okay, right back where they started. So as we go along the tubule of the nephron, remember we said that different parts of the tubule have different functions. So we'll start at the beginning with the proximal convoluted tubule. Remember, looking at the nephron, what vessel goes in? The afferent, right, with an A, right? And then we've got our corpuscle, and then the efferent vessel coming out. And in this corpuscle, that's where we have our glomerulus, right? All of our twisted capillaries. The entrance to the proximal convoluted tubule lies opposite where the afferent and efferent arteriole are. Okay, it's not like an accident, it's not like drawn like that once. This is how it's structured, very intentionally. It's the way it goes. Okay, afferent and efferent are on this side. On the opposite side, we go into the proximal convoluted tubule. Again, we call it convoluted because it's all twisted, and proximal because it's closest to the corpuscle. When we look at the proximal convoluted tubule, we see that the cells that line this part of the tubule have microvilli present. What do microvilli do? They increase surface area. We saw that in the small intestine, didn't we? That microvilli were important to increase surface area. What does the small intestine do a lot of? Absorption. Okay? We said that we needed a lot of surface area for absorption. That's the same reason we have these microvilli present in the proximal convoluted tubule. We have a ton of reabsorption happening here. We'll see that there's a little bit of secretion that happens. We do pump some stuff into the tubule here. But overall, looking at the proximal convoluted tubule, reabsorption is key. When you think PCT, think reabsorption. Active reabsorption. We reabsorb up to 70% of the volume that got filtered out of the blood here. So the majority of everything from water to ions, nutrients, everything that got pushed out gets pulled right back in that proximal convoluted tubule. So when we look at reabsorption, one extremely important thing here is that we actively reabsorb almost every single organic nutrient. Remember I said we should be urinating that stuff out. Glucose, amino acids, fatty acids, these are useful fuels for our body. We do not want to be losing them in the urine all day long. So we reabsorb them almost 100%, and under normal conditions, 100%. So again, that's glucose, that's fatty acids, and that's amino acids. Anything of those nutrients that get pushed out are going to get reabsorbed in the proximal convoluted tubule. We've got active and passive reabsorption of ions. About 60, 65, up to 70% of the sodium and chloride get reabsorbed here. Okay, so again, the majority of the sodium and chloride that were pushed out are reabsorbed. What follows the sodium? Water. And really, it's not just sodium, it's everything, right? We're reabsorbing all that glucose. We're reabsorbing all those amino acids. We're reabsorbing tons and tons of ions. Of course, the water is going to follow. So water is reabsorbed passively, right, just via osmosis. It just follows the stuff. Again, some secretion occurs here. So especially under the control of certain hormones, sometimes we can pump stuff into the PCT, but it's negligible, it's not a huge deal. When you think of the proximal convoluted tubule, I want you to think reabsorption. Okay, reabsorption of the majority of everything that went out comes back in, and almost every single nutrient that we filtered out gets reabsorbed in the proximal convoluted tubule. So after the PCT, we had this really twisted proximal convoluted tubule. Then we get to the nephron loop, right, or the loop of Henle. When we look at the nephron loop or the loop of Henle, remember that it drops down towards the medulla, right, like towards the hilum or the center of the kidney, and then it curves back up out towards the cortex again. When we look at the loop, we can separate it into the descending limb and the ascending limb. The descending limb, remember, is just the first part that goes down. The ascending limb is the part that goes up, right? So the fluid comes from the PCT down the descending limb, it takes this sharp turn, and then it comes back up the ascending limb, and then eventually to our distal convoluted tubule. When we look at these two segments, we see that there is a thick segment and a thin segment present. Some of the models in class show these like really nice and even, and it's not the case whatsoever. Really, the descending limb is almost all thin with squamous cells lining it, and almost the entire ascending limb going up is thick with cuboidal cells lining it. Okay, so the thick segment is seen mostly in the ascending limb. When we look at the descending limb and the ascending limb, we'll also see that the function varies greatly, right? They have very, very different functions, but they actually work cooperatively, right? The descending and ascending limb fuel each other, if you will, or kind of drive the work that each other does. So when we look at the loop of Henle, and we erase my arrows, it's gonna get busy. When we look at the loop of Henle, we see that the descending limb here is permeable to water. That's it. It doesn't have active pumps that move ions or anything else in and out. It simply allows water to flow via osmosis. That's it. Okay, so it's permeable to water. It allows water to flow via osmosis. Now when we look at it and we look at, okay, so where's the water gonna go then? Water's gonna go towards the side with more stuff, right? The higher osmolarity. When we look at the fluid that's coming from the PCT down into the loop of Henle, we see that the fluid coming down should not have any nutrients, right? Why? What happened to all of the glucose and amino acids and everything that were in here? They were already reabsorbed, right? We already took those back into the body in the PCT. What about a lot of the sodium and chloride and stuff? We reabsorbed a lot of that, right? Like 60% or so of it, we reabsorbed. And what we see is that the fluid that's starting to come into the loop has an osmolarity similar to blood. You don't have to know the number, but it's about 300 milliosmoles. So not super concentrated, not very concentrated, just similar to your blood. So as the fluid comes down into the loop and starts to head down, what we see is that the concentration of solutes out here is much, much higher. So the fluid surrounding the tubule, the fluid out here, has a very, very high osmolarity. It's very, very concentrated. So where's the water going to go via osmosis? Out, right? The water goes to the side with more stuff. So we see that as we go down, we reabsorb more water and more water and more water and more water. And as we do that, the fluid in here starts to get more and more concentrated, right? We're not leaving stuff. All the stuff is trapped in there. The solutes are still in there, but we're taking all the water out. So we end up with a really, really high concentrated tubular fluid by the time we get to the bottom here. Again, just because we reabsorbed tons of water as we went down. So let's see here how we can sum this up. Water follows its osmotic gradient, it moves out. So what I would say about that is water is reabsorbed in the descending limb. And again, by the time we get to the bottom, the filtrate has a really, really high concentration because we've taken so much water out of it. Now, when we look at the ascending limb, remember I said that most of the ascending limb was going to be thick segment? So it's going to be lined with these thicker, chunkier cuboidal cells. Water doesn't cross those the same as it does the thin cells. So what we see here is that the ascending limb, as we start to go up, now it's impermeable to water. Okay? Solutes also don't cross via diffusion, again, because we have thick cells. However, we do have active transporters present. So in the ascending limb, we have active transporters that will pump ions, mostly sodium and chloride, actively out of the tube. So sodium and chloride are actively reabsorbed as we go up the ascending limb. Now this is important. What this does is this ensures that we have a ton of solutes out here in this paratubular fluid. Why do we need a bunch of solutes out here in the paratubular fluid? Oh, water, exactly. Okay, so we actively pump sodium and chloride out in the ascending limb. That ensures there's a high osmolarity out here so that water will come out via osmosis in the descending limb. Also, the fact that we pull this water out means that we have a really concentrated fluid, so it's really easy to get these ions, right? It's super, super concentrated, so there's tons of ions there just ready to go in those active transporters. So the two work together in a positive feedback loop. You remember, it's really, really rare to have positive feedback systems in the body. This is one kind of mini positive feedback loop that we have, where this side fuels this side and this side fuels this side, and they kind of speed each other up. Overall, in the loop of Henle, then, we're going to reabsorb sodium and chloride and water, right? We reabsorb between 20 and 25% of the sodium and chloride, which we'd already reabsorbed like 60% of it. So now we have pretty much all of our sodium chloride, or a lot of our sodium and chloride back. And then we reabsorb about 25% of the water. And this is in a typical cortical nephron. What do you think would happen to those values in a juxtamedullary nephron? They would be higher. Exactly. Why? What's a juxtamedullary nephron have? A longer loop of Henle, right? Longer loop of Henle means more water reabsorption. So that value would go up in a juxtamedullary nephron. So what was happening primarily in the PCT? Reabsorption. Reabsorption of 100% of organic nutrients, and then a lot of everything else, right? A lot of water, a lot of sodium and chloride. Most, or a big, huge chunk of the volume of filtrate got reabsorbed in the PCT. Then what's reabsorbed in the descending limb? Water. What's reabsorbed in the ascending limb? Primarily sodium chloride. And this is just showing you that, essentially, this is showing you what we drew here. This does get more specific in looking at the osmolarity. Realize that this is flipped, right? So this is descending, this is ascending. But you can see it's about 300 milliosmoles, just like blood, when we first go in. But we reabsorb water and the osmolarity increases, right? So we've got a really high osmolarity by the time we get to the bottom, and then the osmolarity starts to go down again, right? Because we start to pump ions back out of the tubule, and then the osmolarity is really low when we go into the DCT. That's all we need to mention yet. All right, so that brings us to the distal convoluted tubular, the DCT. Again, we call it distal because it's more distant from the site of attachment, right? It's the last segment here that we see, and then we twist in the tubule. It's convoluted because, again, it is all highly twisted. It's not nice and straight. It's really, really twisted up. So it's the distal convoluted tubule. Again, the last section of the renal tubule. And again, this one passes right between the afferent and efferent arteriole. And again, that's important as well. We'll see that right where this passes through the two arterioles, the cells that are located here, we call cells of the macula densa. And they're going to be really important in forming something called the juxtaglomerular complex. We'll talk about it later, but that's where erythropoietin comes from. That's where renin comes from for the renin-angiotensin-aldosterone system. This is a really important area. So the DCT passes straight through. And again, it's convoluted, so it's highly twisted, just like the PCT, but it's not the same. That's kind of where the structure or the similarities end. When we look at the DCT and we look at the cells that line it, we do not have microvilli present. So do you think reabsorption is super important here? No, not nearly as much reabsorption occurs, which makes sense. We've already reabsorbed almost everything, right? Like 60 to 70% of the volume, or just total volume, was reabsorbed in the PCT. Another like quarter of the fluid was reabsorbed in the loop of Henle, so there's not that much left, right? There's not a ton left, so we don't need all of that extra surface area. The flat surface is plenty for us to reabsorb what we need to. When we look at the convoluted tubule, we do have the secretion of a lot of wastes here. So acids, like hydrogen ion, right, type acids, some drugs, medications, toxins, wastes, a lot of that gets actively secreted or actively pumped into the distal convoluted tubule. So if it didn't get filtered out of the glomerulus, but we need to get rid of it, we can actively pump it into the tubule in the DCT. I really want you to focus on the second part down here, though, when we look at the distal convoluted tubule. So we have a lot of what we call selective reabsorption. And this selective word is important. We have the selective reabsorption of sodium and excretion of potassium. What follows the sodium? Water. So we have selective reabsorption of sodium and water. And again, we trade the sodium and potassium. And what would that end up doing? If we reabsorb a bunch of sodium and water, what would that do to, say, our blood volume or blood pressure? Increase it, right? Increase blood volume, increase blood pressure. And this happens in the presence of aldosterone. This is what selective means. This does not happen normally. In the distal convoluted tubule, it's not typically changing sodium for potassium and doing this all the time. It only does it when aldosterone is present to turn on those transporters. So it's selective. It only happens when we tell it to. How do we tell it to? Aldosterone. Ooh, this should not say this. Cross off calcitriol. That should just say PTH. We also have the selective reabsorption of calcium in the presence of PTH. What's PTH? Parathyroid hormone. When do we release parathyroid hormone? When we don't have enough calcium, right? Blood calcium is low. We want more calcium, so we definitely don't want to pee it out. So we release parathyroid hormone. Parathyroid hormone comes to the distal convoluted tubule, and it says reabsorb all that calcium. So we turn on these channels, right, for calcium, so that anytime we see a little calcium floating through, we grab it and we reabsorb it so that it doesn't go out in the urine. Again, that does not normally happen. These channels are not normally turned on. We only turn them on when parathyroid hormone is present. Calcitriol we make in the kidney, but that goes and works in the GI tract. I don't know why I put that in there. We also have the selective reabsorption of water. This happens in the distal convoluted tubule and in the collecting duct. And this is in the presence of antidiuretic hormone. Antidiuretic hormone comes and it puts aquaporins in. Aquaporins, remember, are just like pores for water, right? They're like little extra channels that water can cross through, and then the water just goes via osmosis. So the distal convoluted tubule is typically not very permeable to water. Water doesn't cross it very easily. Same thing with the collecting duct. Water doesn't cross in and out of that collecting duct very easily. However, when we have antidiuretic hormone here, it comes and it puts these little pores in. Now water can be reabsorbed easily. So then we'll reabsorb extra water. But again, we say that this reabsorption is selective because it does not happen all the time. We have to turn it on, right? We have to make it happen. And we do that with antidiuretic hormone. So when antidiuretic hormone comes and inserts those aquaporins, what do you think happens to blood volume? We increase blood volume, increase blood pressure. What about urine production? Less, right? We decrease urine production because the fluid's not making its way around into the urine, it's being reabsorbed into the body. Again, the key here that I want you guys to remember about the distal convoluted tubule is that this reabsorption is all selective. Okay, this is, again, it's like the last little fine tuning that we do. We've reabsorbed our nutrients, we've reabsorbed most of the volume and the salts and the water, and now it's kind of like, all right, let's perfect this. What's going on in the body right now? Let's do those last little changes that we have to do to keep the body homeostatic. So, urine volume, right, or how much urine we produce is inversely related to how much water we reabsorb. So, if we reabsorb more water, what's going to happen to urine volume? Urine volume goes down, right? And the opposite's true. If we reabsorb less, more stays in the tubule, more wakes its way out, more urine volume is there, right? So those two things are inversely related to each other, urine volume and water reabsorption. Now we have water reabsorption happening in lots of different parts of the nephron, right, and collecting system. It's not just like one area where we reabsorb water. So we can affect urine volume and we can affect water reabsorption in lots of different areas. Now some of this we control, some of this just happens. Some water reabsorption is going to occur no matter what. We can't turn it on and off. So let's look at that. The proximal convoluted tubule, remember we just reabsorb water by osmosis, right? We don't make it happen, we don't turn it on. Like the water just gets reabsorbed with all of the other stuff that's getting reabsorbed in the PCT. Same thing with the descending loop of Henle, right? We don't actively reabsorb that water. We don't have to use a hormone to like insert aquaporins. It just happens. The water gets reabsorbed by osmosis. So the absorption that happens here in the PCT, here, and then in the descending loop of Henle, we call that obligatory water reabsorption. We are obligated to do it. There's nothing we can do about it, right? We can't adjust that in any way. That water is going to be reabsorbed no matter what. We recover about 80% of the volume of filtrate that way. So about 85% of whatever gets filtered out is going to get reabsorbed back in. We don't adjust it, we can't change it, it is what it is. However, remember that the distal convoluted tubule and the beginning of the collecting system, so what I mean by that is the collecting duct, are relatively impermeable to water. Remember we just said water doesn't like to cross those walls unless we do something about it, right? Remember those little aquaporins? We said that if we want to, we can actively insert little pores in the DCT and in the collecting duct, and then we can reabsorb water there, but it's not there naturally. So any water reabsorption that occurs in the distal convoluted tubule in the beginning of the collecting duct, we call facultative water reabsorption. Think of it facultative because we have to facilitate the process. It doesn't happen on its own. It's not natural. We're not naturally going to reabsorb water here. We have to facilitate that process. We have to help it along. Okay, so again, we do that with hormones. We mentioned ADH, right? Which, what does that stand for again?
Antidiuretic hormone.
Excellent, antidiuretic hormone. And remember, diuresis is like peeing a lot. So anti-peeing a lot, right? We're not peeing, we're keeping the water in. How do we keep the water in? We reabsorb it from the tubule. Okay? This amount that we reabsorb in the PCT in the loop of Henle is obligatory. We're gonna do it no matter what, we can't change it. However, we can insert little pores in the distal convoluted tubule and then here in the beginning of the collecting duct. And that allows us to reabsorb extra water to increase our blood volume and increase our blood pressure and keep some of that water, like in states of dehydration or bleeding or whenever we wouldn't want to lose that extra water. Is that okay?